Now we're getting to kind of the meat of springs, which is specifically looking at elastic potential energy. So how is energy related to something that's compressing or stretching and storing energy in that kind of arrangement of the material? So let's talk about elastic potential energy, and it's the energy associated with stretching or compressing an object. And this is only in our case, we're only talking about if the object obeys Hooke's law, will some of this work. So I'll highlight those points for you as we get going. So anything that I put an asterisk next to, that's only going to work if the object obeys Hooke's law, meaning it's an ideal spring. So let's write down our properties. Elastic potential energy is a scalar quantity, just like all energies will be. There's just a certain amount. Direction is irrelevant. The variable we're going to call US, or yeah, US for potential energy. Typically, this U is a one way that we write potential energy. And we use an S for spring. Even though it's not always a spring, it helps us to keep from getting confused with the electric potential energy. Oh, sorry. The units, just like before, are joules. And 1 joule equals 1 Newton meter equals 1 kilogram meters squared per second squared. The equation for elastic potential energy is that the elastic potential energy, and again, we always have to look at changes, the change is equal to 1/2 K times the change, and this is a little bit weird, in the change in X squared, where this is the stretching or compressing from neutral. So in other words, if I have a spring that's naturally 10 centimeters long, and if I stretched it to 15, that would be a delta X of 5. And then if I stretched it from 15 to 20, that would be a second delta X of 10. And if I wanted to compare those two, it'd be the 10 squared and the 5 squared. When we do an example, I'll clarify, and it should be hopefully pretty clear. But again, this is something that might be confusing, so you can ask questions in class. The constant in this example you can see is the 1/2 K, and the indicator is the delta X squared. So in other words, the stretch squared. And I'm using that stretch word lightly. It could also be the compression. But if you square how much you've stretched or compressed it by, that's your indicator. So if we see that it has stretched or compressed by a different squared amount, we'll expect a change in energy. This is very similar to kinetic energy in that if I go from being 10 centimeters stretched to 10 centimeters compressed, there's no change in the energy of that system. Those have equivalent amounts of energy. All right, let's look at a couple examples here. A 0.1 kilogram toy car is propelled by a compressed spring. How much energy is stored in the spring when it is compressed by 4 centimeters, and assuming that the spring constant is 250 newtons per meter. So our delta U spring is equal to 1/2 k times the delta of the delta x squared. Well, if we started with it not compressed, that means delta x initial is going to be 0 centimeters, and delta x final is going to be 4 centimeters. Now, both of these need to be in meters for us to work with our values. Luckily, 0 centimeters is easy to convert to meters, but 4 centimeters is going to be 0.04 meters. So now we can do U of spring is equal to 1/2 times 250. Sorry, let me put the Newton meters in there, put my units in. Newtons per meter times final, which will be 0.04 meters squared, minus 0 meters squared. So the 125 newtons per meter times 0.04 squared meters squared. So that's 0.0116. So it's going to be not something I can easily approximate in my head, but I do want to point out that this will end up giving something with the units of Newton meters, which will give us something with units of joules. So you can go through and actually calculate that, use a calculator to find that value, but that's what we're going to expect is something with units joules. As we've said, with all energy systems, we can only technically calculate the change, but sometimes you'll see that the spring potential energy is blank amount. Like they haven't said the changes, they just say there's 20 joules of energy in this spring. And this is assuming a comparison to the resting or natural state of the spring. So in this case, we could effectively say there's this many joules of spring potential energy because we're comparing it to when it was not stretched or compressed at all.